this week we're talking about. Did I just pause it? Okay. The central limit theorem and the rule of large numbers, right?
Yeah.
Yeah. Distribution of sample means. Okay. Do you have any questions or anything? Do you have any questions?
I don't think so.
Yeah, this one wasn't too bad either so far, at least so far.
Yeah.
Okay. So I've got that website pulled up to do the random integers.
Okay.
So the numbers it gives me are 9, 26, 25, 3, and 16.
Okay.
Nine, 26, 25, 3, 16. So what is the mean of our sample? Yep, go back and get it again. 9 plus 25 plus 3 plus 16. 5. So the mean is 15.8.
Okay. This graph illustrates the sampling distribution of the sample mean. There are 152,506 possible combinations of the 30 salaries, drawn 5 at a time. This graph represents the distribution of all possible samples. Make a mark on the horizontal axis to indicate the value of your sample mean from part A.
Oh, hold the phone.
No, that's not right.
Sorry, we skipped that table. So those are, okay, my bad.
So we're looking for a higher number.
We're looking for those numbers match.
Match with
Yeah.
like 14. Okay,
Yeah.
so really, we remove those numbers.
Are you with us?
Yeah. Sorry, my computer is being weird.
Oh, no worries.
Okay.
So we take those numbers and then we pull the bigger numbers from the table. So that's what we're doing right now.
Okay.
So what were the numbers again?
I did 26, 25. So
So
I'm looking for 16.
give me the numbers real quick. 9, 26, 25.
Is it 9? 9 is 42. Wasn't 16 one of them?
That's 3 and 16. Okay. So number 9 is 45. 3 is
26. Okay, what was the last one?
26, 25. And 9, 3 is 16.
And you just find the mean of that.
Well,
Right?
yeah, you find those mean those 5 numbers.
I don't remember all the numbers, but if I did, it's 45,800.
Yeah, I got 45,800.
Make a mark on the horizontal axis to indicate the value of your sample mean from part A. How do we do that?
I think we have to go to the SPSS to do that, don't we?
Remember that generator that you were playing with yesterday?
No.
And they were dropping?
Stop it.
And you said, let's watch it again, let's watch it again.
Yeah, I don't think that'll do it though.
Honey, can you call the dog? Curtis.
That was the mean.
I think our mean appears to be usual. Curtis,
What's that?
can you call the dog?
Jax.
Go away.
Jax, come here. Come here, Jax. Come on. But you didn't get it. Come on. Come here.
Okay, so we would have to make a mark on the axis, correct?
Yeah, the
Yeah.
horizontal axis. I'm just trying to figure out how to
So,
do that. Can you add like a symbol or something?
I don't know, you're talking to the wrong person.
I think I don't.
Technologically challenged.
Me too.
I don't think you really. I think if you just put your marker there, I don't think you really have to.
Yeah.
44,000, 46 is right in the middle, so 48 or 45800 is gonna be right.
Right
Just-
next to it.
Just the left of it.
I think that would be normal.
Yeah.
It says that a normal sample size is normally 5. Like 5 data.
We got 5 of those.
Yeah. So I'm just saying it aligns with that rule.
Uh-huh. So we're saying it doesn't. It's normal. It's not unusual, right?
Yeah, and then just looking at our data, it all of our data is within that little curve. It doesn't go either to the left or the right of it.
Yeah.
What does it mean to be? What's the definition of usual and unusual again?
Let me see. Okay, so if the population is normal, then the sampling distribution of the mean will always be normally distributed, no matter how many observations are selected. And if the sample is not normal, then the sampling distribution will be approximately normally distributed if the same sample size is large enough.
Okay.
So I think that it's just if our sample follows that normal like bell curve, then it's considered normal. But does that mean that like right skewed and left skewed is unusual?
I think so.
Yeah, I think so. Okay, so we're moving on to D.
So are we ready to move on?
Yeah. So basically we answered C. And then D is compare your mean from question 8A to the means obtained by at least 3 other individuals. What do you notice? I don't know. I'm guessing, because I'm being lazy, but I'm guessing that we'll all have normally distributed. Because all of the information that's given to us is within that bell curve.
I'm betting that the numbers will be the means will be pretty similar.
Yeah.
Yeah.
I'm gonna just do one real quick just to see what it says.
Is it so 26?
No, it's not 26.
So close.
No, it's not one,
27?
no.
That's 29, right?
Yeah, 21 as well.
This one. I'm just like,
Oh yeah, and it says that if the parent population is normally distributed, then your sample will be normally distributed.
yeah.
The mean of this one was 48,120. What was our mean from the last one? So 46.
Yeah, so it's still within that bell curve.
Cool. Okay. So the Graduate Management Admission Test, the GMAT, is used as an admission criteria in many Masters of Business Administration (MBA) programs. The scores on the GMAT are normally distributed with a mean of 529 and a standard deviation of 113. Consider a simple random sample, 10 students taking the GMAT.
Okay. What is the shape of the distribution of the sample means for all such samples? I'm guessing it would be normally distributed.
Yeah, I think so too, just because it should be usual, right?
Yeah. Because the sample that we're taking out of is normally distributed.
Yeah.
Yeah, works for me. That's what the
Yeah, and that's the answer for B.
What did you say?
same
I
answer.
said we answered B as well.
The parent population is normally distributed.
Okay, and then C says, what is the mean of the sampling distribution of sample?
Is this where it's the same as the, like, the population sample?
The mean of the sampling distribution should be equal to the parent population. So it would be 529. Okay, and then it says, what is the standard deviation of the sampling distribution of the sample mean scores for all such samples? So don't you take the
This standard deviation divided by,
square root of the number?
yeah. Standard deviation is 113.
And then the number is 10, so the square root of 10.
I got 35.73.
I think that's right.
Yeah.
Cool.
All right, so you ready to go to the quiz?
Yeah.
Okay.
You guys ready?
Yep.
Mine's just loading, but yeah, go ahead.
When taking samples of n when n equals 5, what was the shape of the distribution of means histogram when the parent population is right skewed?
Should be right skewed, shouldn't it? So it should follow.
I think so.
Yeah.
When taking samples of n equals 100, what was the shape of the distribution of mean histogram when the parent population is right skewed?
Should be right skewed. That's right, isn't it?
Yeah.
When taking samples of n equals 100, what was the shape of the distribution of means histogram when the parent population is normally distributed?
Normal. When would the distribution of means be normally distributed? Data are drawn from a population that is normally distributed and the sample size is small. Data are drawn from a population that is normally distributed and the sample size is large. Data are drawn from a population that is right skewed and the sample size is small. And data are drawn from a population that is right skewed and the sample size is large. I'm guessing it's the first two.
I would think so as well.
It makes me nervous.
I know, I hate these ones.
I'm trying to think. Remember back when it talks about how how small it can be.
Yeah, because I wrote that down, and for a normal sample size, the smallest it can go is 5. And for skewed sample size, the smallest it can go is 30. And then it was like unusual, like in order to get a normal sample size, you'd have to have like 1 billion or something.
So on number 3 then, when it's talking about the sample size being n, the shape of the distribution, that means a histogram, would it still be right skewed at the parents right skewed? You said that has to, you said the sample has to be at least 30.
Yeah. Because,
I think that'd be normal then for number 3.
yeah.
Because I don't know, because if you take 5 numbers, it's gonna be hard for it to be right
yeah,
skewed.
yeah. I get what you're saying. That just clicked with me.
Way to catch it.
Ow, stop. Sorry, I'm not talking to you guys.
I know.
No, it's all good.
I have a little booger.
And 6 would be the first.
Wait.
Sorry, guys.
No worries.
It's all good.
All right. Which of the following gives the best explanation of the central limit theorem? If the parent population from which the data are drawn is normally distributed, then the sample mean and x will follow a normal distribution. For bell-shaped data, approximately 68% of the data will be within 1 standard deviation of the mean. About 95% of the data will be within 2 standard deviations of the mean, and approximately 99.7% of the data will be within 3 standard deviations of the mean. If the sample size is large, the sample will be close to the population mean. If the sample size is large, the shape of the sampling distribution of the mean will be approximately normal. So, the sampling distribution of the sample, this is the central limit theorem. Definition. The sampling distribution of the sample mean will be approximately normal if the sample size is sufficiently large. So I think it's D.
Yeah, that's what I was thinking.
Or yeah, I don't know if you guys want the same.
Okay. Let x be a random variable with population mean equal to 10 and population standard deviation equal to 6. Suppose a sample size of size n equals 36 is drawn from the population. What is the mean of the distribution of sample means?
So is that like what we did? The standard deviation divided by the...
Square root of the number?
Yeah. 'Cause, I mean, that's the only, like, equation they gave us.
Yeah,
That's standard deviation.
that's to find standard deviation.
Oh, okay.
But then number 9 says, what is the standard deviation? So
Yeah.
then
What's the mean of the sample means? There's only one sample mean that we know of, and there's only a sample we know of, and that's 36.
Yeah.
So it's got to be 36.
yeah.
I don't know of any other number that it gives us that wouldn't be that.
So you're saying 8 is 36?
Yeah. I
So the
think.
standard
Hold on.
deviation... Sorry.
It says let x be a random variable with the population mean. So the population means 10. And the population standard deviation is 6. Suppose a sample size of... So there's 36 numbers. Is that what it is?
Mm-hmm.
So there's 36 numbers that are drawn. Is that what it's saying out of the 36 numbers, or is it saying that n is... So 36 is x? You know what I'm saying? Am I confusing myself?
Confusing me.
So you see how it says? It says let x. So it gives x the random variable
Right.
with a population mean. X be a random variable. Population mean equal to 10. The population standard deviation equals to 6. Suppose a sample size. Suppose a sample size n equals 36 is drawn from this population. I guess what I'm asking is the number you pulled is X? I guess the number you pulled out is at 36.
I'm wondering if it's 10 because it says the population mean, and this says sample mean, not sample size. You know what I'm saying? Like the 10 says mean.
Isn't the population mean the same as the sample mean?
That's what I'm saying, yeah.
Yeah, that's what I'm thinking.
So then it would be 10.
Yeah. Because in that question we got on the homework, it was asking what the sample mean is.
Okay.
So then the standard deviation,
I got 1. Because the square root of 36 is 6, and 6 divided by 6 is 1.
makes sense to me. Standard
I
deviation.
know, what I'm thinking.
Oh.
13. Okay, yep. You had to put 1.00.
I think so. It says 3 decimal places, so yeah. Okay, are we ready?
Yep.
Okay, regardless of the distribution of the population, if the sample size is large, what would be the shape of the distribution of the sample mean? So according to sample mean would be the same as the population mean, according to large numbers. If the sample size is large, then the sample mean will typically be close to the population mean. In the central limit theorem, the sampling distribution of the sample mean will be approximately normal if the sample mean is sufficiently large. So I'm guessing it would be normal.
Yeah.
We just talked about this earlier too.
Mm-hmm.
What theorem justifies that?
So you just said that was a central limit theorem, didn't you?
Yeah.
Okay.
I'm gonna check. I'll make sure he's right. Or no, he's right. Oh, he's wrong. At least I should make sense of it in my head. Okay.
Should we submit?
Ready to submit?
Yeah.
Oh.
Whoa.
What did you guys get?
76.
Yeah, same. So on
So
6, we're just missing the last one. Oh, because the sample size is large.
We should have kept number 3. That's confusing though.
I hate how they word it.
Yeah.
That's my bad.
No, you're fine. We can do better next time.
Oh, we should. That's what we should have switched. We should have switched 3 and 4. We should have left 3 normal. We should have switched 4. Dang it. Crap. All right.
Okay, so Thursday.
Yep.
Okay, I can meet at 7 if you guys want.
That works for me.
Okay,
All right,
Cool.
sweet.
See ya.
Bye.
bye.